I changed the title.
Today's speaker is Professor Doron Salvago, who will speak on the following topic. An ounce of symbol crunching is worth a pound of number crunching. Pure mathematicians look down on numbers. They only do symbols. But numbers are very, very, very basic. And numbers could be very, very deep. Take, for example, the following number. The number of self-avoiding walks. I'll explain what it is in a minute. On 1,000 steps. This is a specific, concrete number, and it's easy to write it down once known. It's not too big. It's definitely less than 4 to the power 1,000, which is equal to 2 to the power 2,000, which is roughly equal to 2 to the power 10 to the power 200, sorry. This is not equal to, sorry. It is roughly equal to 2 to the power 3, a little bit bigger than something with about 610 digits maybe. You can easily write it down on a computer once you know it. But this question is much, much deeper, much more interesting than the Riemann hypothesis, than Fermat's theorem, and all the open problems. In 50 years, I'm sure that the Riemann hypothesis will be solved. I'm sure that the P versus NP problem will be solved. Not sure, not for sure, 95%. But I'm much more sure that this problem, this mere number of about 600 digits, decimal digits, would still be unknown. So numbers could be very, very deep. What is a self-avoiding walk? You walk on the plane, and you can go unit steps on the lattice, the so-called Manhattan lattice, and you can walk either right or left, up or down. 4 possibilities. How many ways can you walk from the origin and steps? Since in every given choice we have 4 options, north, south, east, and west, obviously the total number of walks is 4 to the power n, and this gives you the upper bound. But only add the phrase self-avoiding. You walk, but you can never come back to a previously visited site. So you can easily write a computer program to generate all these walks up to 10 steps, even 20 steps, nowadays even 25 steps. Sooner or later, you cannot have all the walks, but the world record is roughly, I don't know now, 120. The only known algorithms for this are exponential time. Not much better than figuring out all the walks and counting it. This is a very, very deep question. So don't look down on numbers, pure mathematicians. I'll be very, you will never ever be able to solve this problem. Very, very deep. So this problem is too hard. So let's consider a slightly easier problem. Goes back to Euler. P of n is the number of integer partitions. Of n. I'll explain in a second. Suppose you have the number 5 in And how many ways can you write it as the sum of smaller numbers? So you can have 5 by itself, that's a number. 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and 1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5, 6. Sorry. 1, 2, 3, 4, 5, 6, 7. I just proved to you rigorously that P of 5 is 7. The number of partitions of the integer 5 is 7. And if you notice, we don't count 1 plus 4 as a separate thing. If order does matter, then the problem is much easier. For example, for 3, it's 3, 2 plus 1, 1 plus 2, 1 plus 1 plus 1. Only 4 ways. For 4, it is 4, 3 plus 1, 1 plus 3. 2 plus 2, 2 plus 1 plus 1, 1 plus 2 plus 1, 1 plus 1 plus 1 plus 2, 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5, 6, 7, 8. So it's 8. For 2, it is 1 plus 1 and 2, 2. For 1, 1 way. For 0, how many ways for 0? One way. There, you do nothing. Empty set. It's an empty partition. So here you can then analyze. You can make a conjecture. 1, 2, 4, 8, and I give you a hint, 16, and then so C of n, the number of composition, is easily, when n is at least 1, beautiful, easy closed form formula. But if you don't consider these as different ones, then the problem is much higher. And it goes back to Euler. Euler defined it. What Euler found was a generating function. He could not find an explicit, nice, closed form formula like this one, 2 to the power minus 1. And nobody knows. It's fine. But what he did was find a nice formula for the so-called generating function. It's an infinite product. Let's write it down. 1 over 1 minus q times 1 minus q squared times 1 minus q cubed times dot 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 1 minus q to the power n times dot 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 forever after. An infinite product. But infinite, quote unquote. Euler did not care about convergence. Euler was smart. He just did things formally. Then stupid people like Cauchy and Weierstrass criticized him for his lack of rigor. But it turns out that Euler was right and they were wrong. All the analytic theory is completely irrelevant for combinatorics. These are all formal power series because you look at the collection of all partitions. I have to decide how many ones. I have a collection of ones. Is there no ones? Or 1 1, or 2 ones, or 3 ones? I have a choice. And the formal power series of this decision, how many ones to pick, is that 1 plus q squared, da 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 da. A geometric series, which is 1 over 1 minus q. As a formal power series, not, and some people always write, the q less than 1, analytic convergence. This is so irrelevant. and these people are stupid. Because it's completely irrelevant. There's a form of power series. And the dot is a finite object. As you know, as some of you know, I don't believe in infinity. So when you write 1 plus q plus q squared plus all it means equals 1 over 1 minus q. All it means that if you multiply both sides by 1 minus q, you get 1. 1 plus q plus q squared plus minus q minus q squared minus q plus cancellation, and the only survival is 1. So this explains this. Now completely independently, you decide how many 2's. No 2's, 1 2's, 2 2's. So you have another form of power series. And thus these atomic decisions of how many 2's to include is a no 2's or 1 2's explain for this. And these are completely independent. And then you look at the collection of infinite quote unquote. The weight and numerator is exactly this. So this is the proof of Euler's beautiful thing. And this can be used to compute on a computer the first maybe 50,000 terms. Nowadays, with Maple, you go and have a command called Taylor. And then the MUL for multiply. 1 over 1 minus q to the power I. And going to infinity, if you want the first 50,000 terms, then 1 over 1 minus q to the power of 50,001 is completely irrelevant. Because it starts with 1 plus q to the power of 50,001 plus q to the power of 10,002, so it will never show up. So you do 1 dot dot 50,000. And lo and behold, you get the first 50,001 terms of this series. But please don't try it. It's not a very efficient way. It's a way, but not a very efficient way. The same Euler was a very smart guy. And he found a much better way of computing fast a table of P of n. He had a beautiful recurrence. P of n equals P of n minus 1 plus P of n minus 2 plus dot, plus minus j, sigma over j, goes from negative infinity to infinity. But remember, this infinity is a with a grain of salt. P of n minus the so-called triangular numbers. So we don't even need this. Well, it's better to write like this. Equals 0. So when j equals 0, it's one of them. So now, if you know the previous terms, so you have P of n equals P of n minus 1 plus P of n minus 2 minus, and it turns out it's only the roughly square root of n terms. So this is a much better way to crank out. And about 100 years ago, the great combinatorialist, Major Percy McMahon, used this Euler recurrence to compute by hand. He was a great mathematician, but also he loved computing for its own sake. A table of the first 200 terms. And this is very, very famous because the famous Indian genius Ramanujan looked at these tables and made some observations that the famous Ramanujan congruences, that P of 4, P of 9, P of 14, and so on, are always divisible by 5. And same thing, analogously with 7. I think it was 5. Then later Ramanujan proved it, but he first conjectured it using the tables for this. So even for hand computations, this is good. But what about computing P of a googol? I was just curious how to compute these beautiful things that McMahon used to compute the first 200 terms, and nowadays could be used. My computer can easily, in 100 seconds, do, I think, 100,000 terms. And if I let it run all night, it can probably do 300,000 terms. But it cannot do a googol for two reasons. First, using this recurrence, you would need roughly the square root of a googol, which is 10 to the power 50 operations, and this is beyond the scope of today's computers, even a much better computer than mine. So it's hopeless to get the P of a googol using this recurrence. But there's another reason. Can anybody tell me another reason?
Numbers are too big.
Yes! Even if God told us the exact value of this, we would not be able to store it. Because the same Ramanujan, together with Hardy, proved an asymptotic formula, the order of magnitude, which is roughly, I don't remember exactly, you can look it up, but it's e to some constant involving pi square root of n. So let's compute roughly what it is. Let's pretend that e to the c is 10. What is the square root? So 10 to the power 50. So the answer, if you knew it, would be an integer with 10 to the power 50 digits. And there's no room in our universe to have this. So this is completely hopeless. So what would you do? I was very curious what happens if instead of allowing an arbitrary integers, you have restriction. So what if you look instead of P of n at the related quantity, the number of partitions of n with at most m parts. So you want to split up a number, but you restricting the number of summands. So this is P sub n of n also goes back to Euler. The number of partitions of n into at most m parts. And using exactly the analogous consideration, the generating function also goes back to Euler. Does not go forever now, because now our options are either use 1, as many as you want, you can use as many times as you want to, and the largest part, so it's equivalent to the largest part. It's well known, it's easy to see that this is the same thing now, this of n with the largest part. Then with all constituent parts, this is an easy exercise for your homework. So now you don't go forever. You decide how many ones, how many two, da da da, and oops, sorry. 1. So you also have this.
You have Q to the M on the top, right? The last one.
Q? No, it's fine. No. It's most.
Oh, at most.
It's most, it's my most, yeah. So you can do the same thing with maple. And I was curious, just curiosity, I love numbers, I love explicit numbers. As a computational challenge, what is p sub 60 of 10 to the power 100? In how many ways can you take a googol and break it up into smaller parts, but the largest part is more 60 parts? If you use this command, this multiplication, this maple, it's hopeless. There's another way. If you look at a classical way of writing partitions, is in terms of the so-called Ferrari diagram. You write the number of dots. For example, let the partition 5 plus 4 plus 2 plus 2. So now the restriction is that the number of parts is at most m. Now there's no analogous, but there is analogous thing to this, but it's not so nice. The obvious way is to, instead of focusing on 60, to look in general for a recurrence relation expressing p sub m of n, the number of partitions of n into at most m parts, expressing it in terms of the same thing with smaller m and or n. So, suppose we look at a typical partition that had the largest part is at most m. Or not, okay, either the largest part is at most m. There are two possibilities. M shows up or M does not show up. If M does not show up, then it's exactly the same problem as the number of partitions of n into at most parts with at most m minus 1. So this is the case 1, where m does not show up. If there is at least one copy of m, we can remove it. There's possibly some more copies. If we remove it, we reduce the problem to counting the number of partitions into at most m parts. We are allowed to have multiple, but now we have removed m. So you have a nice, simple, good-looking recurrence that expresses p sub m of n in terms of the same thing with either smaller m or smaller n. And you can write a little code in your favorite programming language. And in Maple, you should do option remember whenever you have a recursion. And you need initial conditions, of course, obvious one, and you can crank out a table of p to the power mn for m between 1 and 100, and maybe n between 1 and 1000. But if you try to use this to find my object of desire, p sub 60, you'll never finish. This recurrence, we have to remember everything previously with the googol and this. So what should we do? I'm really, really desperate to find out. So, in collaboration with Andrew Sears from Georgia Southern University, who gave a beautiful talk in the summer when he was visiting here, we tried to figure out an efficient way to compute p sub 60 of a googol. We found it, and we were very, very proud. And the ideas were really, really old. The ideas that Andrew, as a duo, told me about go back to Kaylee and Sylvester. But they didn't have a computer. So using the ideas of Kaylee and Sylvester, plus modern computer algebra system, maybe in our case, we found the exact answer to this. And this is right here, only 2 pages. It's about 5,738 digit number. It starts like this: 8, 6, 6, 5, 6, 5, 8, 1, 2, 9, 9, 4, dot, 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 And the last few digits are 0, 3, 8, 8, 5, 4, 0. And we got it by number crunching using 0.04 seconds. We were very, very, very proud. We were sure that nobody else in the whole world who doesn't know about our new ideas that goes back to Kelly and Sylvester, but nobody ever bothered to read Kelly and Sylvester. People are too busy reading what's been done 2 years ago, so they don't never go back to Kelly and Sylvester. They have great, great ideas, but they didn't have computers. So Kelly and Sylvester, in fact, you don't need Sylvester. Kelly plus computers can do much more. They were very, very proud. And I was curious if anybody else could do it. There is a new, relatively new forum called Mass Overflow that I strongly recommend. That anybody can ask a question, interesting questions. But beware, you could get, it's very dangerous. The people who use it are very opinionated. If you don't like a question, they can knock it down. And then there is another version called Meta Overflow. It's called Mass Overflow. So you can propose, anybody, you can be a user, but anybody can just go to, you just Google Mass Overflow. If you have a question you want to know, and I didn't know about the ethics of, the etiquette at least, of Mass Overflow. You're supposed to answer a question that you do not know the answer. It's a great tradition in mathematics to challenge other people. Like Fermat, when he wrote correspondence to British mathematicians, he already knew the answer. It was a challenge to see who is smarter. But they didn't like this. So they suspected that I already knew the answer. So I offered 10 square US dollars for the first person that in 1 week would compute this number with 5,738 digits. It's in floating point, 0.8665. And I offered $100, and I thought I was safe. I almost was tempted to offer $10,000, but I knew it would be tacky to offer $10,000. It's not good taste. I was sure that my $100 was safe. Because who would read Kelly and Sylvester and use it together with Maple or Mathematica? To my dismay, about a few hours after this, not the whole week, a user called Joro. I know his real name, but he doesn't like to be revealed. It's another thing of the nerdy hacker culture. They use the username and they don't like to use the real names. So I know the name because he had to write me email. Because I told you have to write me email if you know the answer. But Joro came out with the exact answer. And I accepted. I was hoping it was a mistake. I was hoping that he cheated and used floating point. And the dot here in the middle were wrong. But I didn't take all the digits. But I took some random digits in the middle. And it's exactly. And he was very, very proud. It only took him 2 hours using Paris on a big computer. Paris is a computer algebra system that does number theory. Not say computer algebra, it's for number theoretical computation. So we were a little bit disappointed. It could be done. But still, 2 hours, it's much longer than 0.04 seconds. And to be honest, before we could do this with number crunching, we had to do a preliminary step that I'm going to talk about called symbol crunching. And this is my point. With an investment of 300 seconds, of symbol crunching, you can find a symbolic, explicit, algebraic expression, not just for this one number, like Joro did, but a general formula for p sub 60